Welcome to the Problemers channel Season 1 Episode 5, the episode in which we will discuss the solutions of the three fun and easygoing problems, and the episode in which we will discuss the solution of the official mathematical problem S1M3. As a reminder, at the end of the previous episode, we suggested that you guys try to throw a sheet of office paper across, let's say, your living room, or for 10 meters, 10 yards, or 30 feet out for demonstration purposes. Then we suggested that you try to carry some amount of water in a sieve. And then we suggested that you write a little bit of clever code that programmatically detects whether an unsigned integer named x is a perfect power of 2 or not. Beginning with the first problem. It may seem that that problem is either next to impossible or very difficult to solve because the aerodynamic properties of a regular sheet of office paper are not very agreeable with the task that must be carried out. However, with a clever application of the transform and conquer problem-solving approach, which we discussed in the previous episode, it becomes possible to unlock several solutions of this problem. As an example, the very first solution could be as simple as taking a sheet of office paper and crumbling it into a ball. Then this modified or transformed sheet of paper becomes a ball, and the aerodynamic properties of such a ball are much more agreeable with the task at hand. In other words, such a paper ball can be thrown across a living room, for example. Then at the place where the ball lands, we pick it up, we unfold it, and present the original sheet of paper in its intact form. Again, we explained how the transform and conquer problem-solving approach works in detail in the previous episode, where we were very slow, thorough, and methodical. From that point onward, we will step a little faster, but it is always a good idea to ask the three fundamental questions about a candidate transformation. In this case, we inquire, is the transformation of paper by crumbling it reversible or not? And the answer to that question is yes, of course. We can always unfold that sheet of paper back into original, as long as we take care not to rip or tear that sheet of paper while we are crumbling it, which is pretty much the same thing that we did when we were creating a net of a cube in the previous episode. Second, we inquire, does this transformation preserve the technical essence of the original problem? And the answer is, again, yes, of course it does, because as long as we do not alter the particular sheet of paper in any way, shape, or form, then once we unfold it, that sheet of paper, then it becomes the original sheet of paper. Lastly, we inquire if this particular candidate transformation affords us any technical advantage, and the answer is, again, yes, it does, because precisely the aerodynamic properties of a paper ball are much better and much more agreeable with the task at hand. As a second solution that is slightly more sophisticated, what's possible to do is increase the weight of a given sheet of paper artificially by wrapping a small rock inside that sheet of paper. However, with this particular solution, we will be carrying out not one transformation, but how many? Correct. In this particular case, we will be carrying out two transformations in succession. The first such transformation will be the act of loading a small rock into a sheet of paper. And once that rock is in the sheet of paper, the second transformation will be the good old process of crumbling it. Once this artificially more heavy paper ball is ready, we can throw it the required distance across the room, pick it up on the other side, unfold it, and perform the reverse transformations or untransformations in reverse order by first uncrumbling the sheet of paper and by removing the rock from it. In other words, in this particular case, in plain English, very quickly, we can say that we rock, crumble, throw or solve, uncrumble, unrock. Now, it may seem that this business of wrapping sheets of paper with the rock in it is childish, but this is not the case because, for example, with this particular exercise, it becomes easy to see how naturally symbolization of mathematics emerges in mathematics. For example, let's say we symbolize the transformation of putting a rock into a sheet of paper with the uppercase letter R. And we symbolize the transformation of crumbling the sheet of paper with the uppercase C. Then, how can we record that particular string of operations where we first put a rock into a sheet of paper, then we crumble that sheet of paper with a rock in it? Well, that can be done with the help of the mathematical operation known as composition, which is usually symbolized with a small circle like so. And in the modern notation, such a string or a composition of two operations is parsed or carried out right to left, when the very first operation that's carried out in this composition is the rightmost one, or putting a rock into a sheet of paper in this case. And the output of this rightmost operation becomes the input for the next or leftmost operation. Once our paper ball reaches its destination, we pick it up, we reverse transform or untransform that particular solution of the easier or transform problem in reverse order. That is, we first uncrumble the given sheet of paper, and we can symbolize the process of uncrumbling with the -1 notation, which represents a reverse operation. And we can represent the removing rock from the uncrumbled sheet of paper with -1 like so. As an example of how these childish manipulations of rocks and paper become grown-up mathematics, as an example, in the theory of groups, there is such a thing that is called a commutator of two group elements x and y. And formulaically, such a commutator looks precisely like these guys that we looked at a minute ago. And by definition, the commutator of two group elements xy is exactly the formation of x times y times x to the -1st times y to the -1st. Also, let's say we symbolize a given problem, perhaps difficult to solve problem, with a symbol P. Then the act of finding a successful transformation and applying the transform and conquer problem-solving approach to this particular problem can be symbolized as a letter T, T followed by P, and this gives us a new solution of the transformed problem. Then to this solution of the transform problem, we can apply the reverse transformation as this particular problem-solving approach prescribes, -1. And this particular formation of group elements is one way how the so-called normal subgroups of a group come into existence. Very well, as a third solution of the first problem, I hope that some of you guys managed to come up with a very elegant, if not to say exquisite idea of folding a given sheet of paper into a paper airplane, like so. Again, in this particular case, we inquire, does this particular operation of folding a sheet of paper into an airplane is reversible? And the answer is yes, of course it is reversible, because we can always unfold that particular airplane back into the original sheet of paper. Next, does this transformation preserve the technical essence of the original problem? And the answer is yes, again, of course it does, because we take care to not rip or tear or cut the given sheet of paper when we form an airplane. Lastly, does this transformation afford us any tactical advantage compared to the original difficult to solve problem? The answer here is, of course, yes, again, and there exists a great variety of paper airplanes, and some such airplanes are optimized for speed, in which case the surface area of the wings, these guys right here, is made a little bit smaller by folding them higher or further away from the center line. And some such airplanes are optimized for distance, in which case the surface area of the wings, these guys, is made slightly larger than average by folding the wings like so, closer to the center line of the airplane. And this looks like exactly what we need in this particular problem. We would like to optimize the construction of a paper airplane for distance and send it quite a bit, many units of distance out. As such, we're done with the first problem, and we will discuss the solution of the second problem next. The objective of the second fun problem was to carry some amount of water in a sieve or in a colander across a room. Again, at first blush, it may seem that this problem is either next to impossible to solve or very difficult to solve. However, now that we know the mechanics of the transform and conquer problem-solving approach, a search for a successful solution of this problem becomes much more tractable. Indeed, in this particular case, a successful transformation turns out to be the rearrangement of the state of water from liquid into solid. In other words, in this particular case, we simply freeze a given chunk of water in the refrigerator. Then we put the frozen water into colander. Then we carry water in the sieve across the room the required distance, and then we position that sieve over the original vessel and wait for the ice to thaw, and with us solve the given problem. Again, you guys should go over the three fundamental questions of the transform and conquer problem-solving approach on your own at this point and explain to yourself why this particular transformation is reversible, why does this transformation preserve the technical essence of the original problem, and why does this transformation affords us a tactical advantage. Meanwhile, we will move on to the solution of the third fun problem. The objective of the third fun problem was to detect programmatically at runtime whether a given unsigned integer named x is a perfect power of 2 or not. Again, in this particular problem, it is possible to come up with several solutions, and some such solutions could be quite awkward and not professional or not maintainable, but a clever and professional and maintainable solution can be uncovered precisely by applying the transform and conquer problem-solving approach to this particular case. In detail, if we look at the perfect powers of 2 represented in their base 10 format, 1, 2, 4, 8, 16, 32, 64, 128, and so on, then that information is not particularly helpful because that format is not precisely revealing what do we do with it. However, the moment we transform that number from its base 10 representation into the corresponding base 2 representation, then we see that all of a sudden an actionable pattern emerges. Why is that? Well, in base 10 representation, these numbers look as follows, but in the base 2 representation, we see that each such representation carries only one symbol named 1, here, 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 and here, and all the remaining bit positions in these representations are filled with zeros. Before we decide what to do with this interesting information, let us ask the three fundamental questions of the transform and conquer problem-solving approach. First, is this particular transformation reversible? And the answer to that question is yes, of course. Given a number in its base 10 form, such a number can always be converted into the corresponding base 2 representation, and in the opposite direction, given a number in its base 2 representation, such a number can always be flipped back or converted into its base 10 representation. Second, does this transformation preserve the technical essence of the original problem? The answer here is also yes, and for the following reason. A number in mathematics is a rather abstract notion, an abstract entity. As a matter of fact, a number in mathematics is so abstract that it is very challenging to pin down a short, concise, and crisp definition of what a number is in such a way that all the mathematicians in the room will agree on that definition. As such, in mathematics, what a number is frequently left undefined. What that means is that a number in mathematics exists totally independently and in complete separation from its representation. For example, this here symbol 4 is not the number 4, but rather a symbolic representation of an abstract entity known as the number 4. Likewise, this here symbol 2 is not the number 2, but a symbolic representation of the abstract notion known as the number 2. Consequently, it doesn't really matter in which specific base a given number is presented to us, base 10 or base 2 or base 3 or base 17 or base 59, it doesn't really matter because that number remains one and the same. Third, does this particular transformation provide us with any sort of tactical advantage? The answer here is also yes, and for the following reason. The moment we transform a perfect power of 2 from its base 10 to base 2 representation, then to that particular representation, we can apply all sorts of computer scientific material. For example, we can subtract number 1 from a perfect power of 2 and obtain a result. In the base 10, that result, for example, 4 minus 1 equals 3, again, is not very revealing. It's not really clear. What do we do with this particular number? However, in base 2, we see that what's happening is the following. Each and every bit to the right of the original bit 1 gets flipped from 0 to 1, as shown here and here. The original bit 1 itself is flipped into 0, and because there were no 1s to the left of 1, this situation remains. In this case, we get 3 zeros and 2 1s in the rightmost positions. And what does that mean? That means that if we bitwise AND a given integer x with its own image reduced by 1, in other words, if we say x bitwise AND x negative 1, then what will result? Well, let us do this operation together. 0 and 1, 0, 0 and 1, 0 again. 1 and 0, 0 again, and the remaining zeros become zeros. In other words, what we notice over here is that if we perform a bitwise AND operation of the original number that is given to us in base 10 with itself reduced by 1, then 0 will or 0 must result if such an integer is a true and genuine perfect power of 2. In the opposite direction, if the given unsigned integer x is not a perfect power of 2, then somewhere over here in this result, there will be an imposter named 1. Somewhere here or here, it doesn't matter, at least 1 will show up, and the result of this will not be 0. Consequently, our little bit of C-like clever code reveals itself. In such a code, we declare, for example, in C, in the absence of the dedicated Boolean data type an integer, it doesn't really matter. We call that integer is power of 2. And at first, we demand that this unsigned integer x is not 0 because no positive perfect power of 2 can never be 0. And then we end this result of this operation with what we observed earlier, where we take the original unsigned integer x, bitwise ANDed with x reduced by 1, and demand that the result of this bitwise AND operation must be 0. And in this one line, we return the integer is power of 2. And in this particular case, the reverse transformation is really trivial. We don't have to do it. We can refer to it as the identity transformation because the answer is evident from this string of operations without a dedicated reverse transformation, and the problem is solved. Before we deep dive into the solution of the official mathematical problem S1M3, I would like to say that those of you guys who successfully solved the previous 3 fun, relaxed, and easygoing problems correctly and on your own had to do at least 2 things correctly. First, you had to understand the mechanics of the transform and conquer problem solving approach to begin with, and then you had to successfully apply that understanding to a live setting, so to speak, by applying that knowledge of how the particular problem solving approach works to a specific problem. And that was my idea to begin with, because I specifically designed these problems to be void of highly specialized mathematical terminology, and I kept these problems as simple as possible, but not simpler, because in order to understand how this or that notion in mathematics works, we do not really need to use highly complicated or complex problems. Simple examples and simple problems work, and as soon as we gain a deep understanding of this or that notion, there is no limit to the complexity of the consequent problems to which we can apply that understanding. Case in point, in the problem S1M3, the objective was to find a shortest possible circumnavigating orbit of our friendly and inquisitive end over the surface of a cube when this end starts at the point P that is specifically displaced from any vertex of that cube. Again, this problem seems to be very difficult to solve because it's in 3 space. We need to somehow circumnavigate the cube by visiting each and every face of that cube. That is a fairly strong constraint on that problem, and it is not really clear how we can do that right out of the gate. However, armed with the knowledge of how the transform and conquer problem solving approach works, we understand that the search for a solution of this problem can become tractable. That is, in this particular case, we can cut our cube open into a net that has a shape that is different from the cross shape that we obtained in the previous problem. That particular shape will not work. and it's a good exercise for you guys to understand why this shape will not work. But this specific net, as shown over here, this one right here, that looks like, for example, 3 dominoes stacked one on top of the other and shifted by one face of a cube, in this particular case, is a winner in any position that you look at it. I'll show it to you guys this way and this way, like so. And note that in this particular case, I did not cut any flaps in this particular net of a cube. As such, the resultant cube is quite flimsy, but you can see the magic of how a 2-space object becomes a 3-space object without any flaps, somewhat flimsy. And in the cube that I showed you guys in the previous episode, I did have the flaps. There's these guys right here, this and this and this. And of course, you guys should understand that these flaps are not a part of a net. This is just purely utilitarian additions. We apply glue to the surfaces of the flaps when we glue the corresponding solid together. Now, let us try to answer the following question. Why the proposed circumnavigating orbit is the shortest one? Well, in this particular case, the original point P, because it belongs specifically to an edge, and we know that 2 faces of a cube share a single edge. Consequently, as we noted in the previous episode, when we cut a cube along that edge splits into 2. Precisely because our point P sits on an edge like that, then that point also splits into 2 distinct copies of itself. For example, a point P here and a point P here. Thus, we have 2 distinct points in the plane, and the begging question here is what? What is the minimizing geodesic in the Euclidean space in general and in the Euclidean plane in particular? Well, by now we know well that such a minimizing geodesic is a straight line, and that straight line guarantees the minimality of the distance between these 2 points. Also note that this particular circumnavigating orbit visits all the faces of the given cube as requested. On the first leg of the journey, we visit this face. On the second leg of the journey, we visit this one, then this face, then this face, and this face, all accounting for all the faces. Now, let's try to compute the length of that shortest circumnavigating orbit that visits each and every face of a cube. What do we see here in this particular net of a cube? Well, we see that this orbit will be bound, so to speak, between 2 diagonals. This diagonal over here, that is comprised of 3 diagonals joined end to end, and this diagonal that is also comprised of 3 diagonals that are joined end to end. Consequently, as the point P runs back and forth anywhere along the edge of a cube, the corresponding point P over here will also run in tandem, and a shortest circumnavigating orbit that touches all the faces of a cube will also move with these 2 points, consequently bound between this diagonal and this diagonal. Now it becomes easy to answer the question of what is the length of that shortest circumnavigating orbit that visits all the faces. One diagonal of a square with the side A, as I showed over here, A, we have A all over the place, is simply A scaled by the square root of 2. And because here we have 3 such diagonals stacked one to the end of the other, that number will be also scaled up by 3, and that is our answer. the shortest possible length of the circumnavigating orbit over the surface of a cube that visits each and every face is 3 times a times a square root of 2. Now let's analyze a little bit what happens if the initial point of the circumnavigating journey is a particular vertex of a cube, for example, this one and this one. Well, in that case, if we demand that such a orbit is shortest in length, then it must be a straight line, and that straight line over here will be exactly 3 diagonals joined end to end. And let us see what happens in this case. In this case, our friendly end will only visit this face, and this face. But our end will have no chance to visit this face, and this face. And that will be the violation of the constraint that our circumnavigating orbit must visit each and every face of a cube. Consequently, if our end starts its circumnavigating journey from this vertex of a cube, then what will happen? Then, if we demand that such a orbit is shortest in length as possible, then that orbit must be a straight line, which will be again 3 diagonals stacked one to the end of the other. And on this particular journey, yes, the end will circumnavigate the cube, but it will only visit this face, and this face, and it will not visit these 3 faces over here, thus violating the constraint that each face must be visited on that circumnavigating journey. In order to help you guys visualize a little bit what is going on with the position of the point P on an edge of a cube, I put together a small animation with the software called GeoGebra, which I captured with the software called Kazam, which I invite you to watch right now together with me. Now that we understand how the shortest circumnavigating orbits behave as the point P runs back and forth along an edge of a given cube, I want to make sure that you understand that in the two-space view, or over this particular net of a cube, such shortest circumnavigating orbit runs parallel to the 2 given diagonals over here. And what that means is that the displacement, or let's say horizontal displacement, of the point P with respect to, say, this vertex, or the distance between this point P and this vertex of a cube, is precisely the same as the distance between the body point P and this particular vertex of a cube, which means that that straight line from P to P is parallel to these 2 diagonals in this particular net of a cube. Consequently, in order to obtain a complete solution of the problem, we know that the transform and conquer problem-solving approach suggests that we perform the reverse transformation, and in this particular case, it simply means that we have to draw the straight line, for example, well, it's a little bit different here, which I did with a marker and a straight edge. And now we simply fold this particular net back into a cube. It will be quite flimsy because, again, I did not cut any helper flaps for this particular cube, but hopefully you guys can see that the 2 points P and P meet at the same spot, and we thus have our circumnavigating orbit that is shortest in length and which visits all the faces of a given cube, and the problem S1M3 is solved. Before we abandon a cube and start working with a regular tetrahedron, I would like to expand your mathematical horizon a little bit and possibly motivate the further and deeper study of mathematics by saying that it is always a good idea to construct several models of a cube, like I did over here. I have plenty of those. This is a small one with the numbered vertices. This model over here is of the same color. And this particular model has all the faces of a cube of different color. And it is a good idea to have at least two of these guys, because with at least two cubes where all the faces have different colors, it becomes possible to study the introduction into the theory of groups by studying the so-called rigid symmetries of a cube. In a lightning round, what is a rigid symmetry of a cube? A rigid symmetry of a cube is such a geometric transformation that takes a cube back into coincidence with itself. For example, imagine that this particular cube has the axis of rotation that goes vertically like so, and around that vertex, or about that, axis, we turn the cube by quarter of a turn or 90 degrees, like so. By turning a cube that way, we take it back into coincidence with itself, and that particular rotation becomes an element of a group of nothing but rotations of a cube. That particular group has 24 elements in it, and that group is isomorphic to the so-called symmetric group S4. And it is also possible to study the group of rotations and reflections of a cube in 9 of its planes of symmetry. Consequently, in the group of rotations and reflections of a cube, there will be 48 elements, of which 24 will be rotations from the previous group, 9 will be reflections in the planes of symmetry, 1 will be the so-called central symmetry, because a cube is a centrally symmetric figure, and there will be 6 and 8 or 14 so-called reflective rotations, which are very interesting geometric transformations in their own right. Are you guys ready for your next challenge, which will consist of 2 problems, of which one will be fairly simple for you at this point, and the other one will be very difficult, and that second problem will be so difficult that I mark it with 2 stars. As such, in the first problem, S1M4, the objective is for our friendly and inquisitive ant to find a shortest circumnavigating orbit around a regular tetrahedron with the edge length of A, such that that orbit visits each and every face of the given tetrahedron. You should have not too many problems solving this particular challenge, but spend a good amount of time on the solution of this problem, because the next problem, S1M5, will be so difficult that I gave it 2 asterisks or 2 stars. And in that problem, we suggest that using the ideas and the material that you will uncover while solving this particular problem, S1M4, and the solutions of all the previous problems where we employed the transform and conquer problem solving approach, you should try to invent, that's a difficult part, and solve, this is also a difficult part, a problem that is related to the situation that is unfolding in the problem S1M4. If you can find the intended problem in S1M5 challenge, then you are doing very well. But if you cannot do that, then don't worry. This is a very difficult task. Maybe you can even treat it as optional. If you cannot do it, then you can skip it. But if you still want to give it a go, I'll give you guys 2 hints for the problem S1M5. When you will be solving the problem S1M4, you will, hopefully, uncover a successful, shortest possible, circumnavigating orbit over the surface of a given tetrahedron that visits all the faces of that tetrahedron. And then that particular orbit will do something interesting with the edges of the given tetrahedron. Try to think what that interesting is and how you can apply that knowledge to the solution of the problem S1M5. As a second hint, if the first one is not too helpful, then you will find that the specific circumnavigating orbit around the faces of the given tetrahedron will mark certain points on the edges of the given tetrahedron. The question is what these points will look like and what other mathematical or geometric object will they delineate, and what this object will do to the overall volume of a given tetrahedron. In other words, as a second hint, the intended problem that you should invent and solve over here in the challenge S1M5 has something to do with the volume of the tetrahedron, and that something is actually quite elegant and quite beautiful. As an extra, you should try to actually construct the resultant ideas, again with project or heavy paper, and share your creation with us. This is it for this episode. Thank you very much for staying with us. Thank you for your time. I'll see you guys in the next episode where we will discuss the solution of the problem S1M4 and the solution of the challenge S1M5.